Okay, great. So just to begin, I want to thank the organizers for putting together a really fascinating and, to be honest, challenging program. I've learned so much these last few weeks, and I'm really grateful also to have the chance to speak today. And today I'm going to talk about a problem that I've been thinking about over the last few months. To be honest, I've been more obsessing about it, and this is very much work in progress. So I'm a bit trepidatious about sharing with you, but I think we're all a close community, and I'm not going to be too worried about it. So the topic is matrix permanence and determinant in as kind of a reference point. And so I'll start off with a quick review, and then talk about how you can map this problem to an eigenvalue problem, and then talk about how you might reduce the dimension of that eigenvalue problem, and then show a mapping to bosons and fermions that I think is kind of cool and maybe you haven't seen before. And then I'd hope to talk about about quantum algorithm for the matrix permanent, but I think I have way too much stuff, and I probably won't get to it. So my plan is just to put these on the workshop website, and then things that I skip you can fill in, and I'm happy to answer any questions. So I probably won't get to the quantum stuff, even though this was literally my motivation for studying this problem, was coming from the quantum algorithms perspective. But then I got sidetracked by a whole bunch of interesting issues in the classical case. I have way too many slides. I have 66 slides, and so I promised Tino that instead of speaking twice as quickly as I usually speak, which is really quickly, I'm just going to try to keep it slow and then just skip a whole bunch of stuff. Especially, I'm going to skip a bunch in the introduction, and you can read it, and I think it's all going to be very easy. And then so that I can get to the really interesting stuff. Okay, so that said, right to the introduction. So I'm going to start with the determinants, which are much more familiar, and we have some matrix M of dimension n, and the matrix elements are labeled W's because I'm going to relate them to edge weights of a graph later on. And then the definition for the determinant is given. It's all something we know and love. It's a sum over all the permutations of products of matrix elements in different rows. And there's also a sign that you have to take into account, which counts either even or odd numbers of permutations from the reference. So basically, this is, you have n factorial contributions generically to that sum, and I think it's kind of an amazing fact that despite the fact that there are n factorial terms in the determinant, it's still computed in a polynomial time so classically efficiently. And I think the record is n to the 2.373. I want to just very, very quickly just show how the naive one works for n equals 3. You use a Gaussian elimination or pivoting, and you take this matrix, you multiply by some constant on the second row, and that way and subtract then the bottom row, and that allows you to produce a 0. You get this kind of row echelon form. And I'm only mentioning this because there's going to be a quiz later about what these actual factors are. So there's the first round, you do this twice, once for the bottom row, once for the second row. That gives you these rescaled weights. And then you can also look at it a bit more intuitively as you have the initial index. The first index of the W is 0 and then 1, but then the second one changes from 0, 1 to 1, 0. And so that's one exchange, and that gives you that minus sign. So it's a bit clear there. And then you can do it again. That allows you to produce a matrix in a upper or lower triangular form, and then the determinant is just the product of the rescaled weights. And then I just expanded it for you just to make a point, which is that there are 8 terms here, right? There's 4 here and there's 4 here, but we only want 6. It's only 6 because 3 factorial 6. And so this is this amazing fact that this term, so W11 times this term, exactly cancels the W12 term times this one, and that reduces the 8 terms to 6, and bingo. And it turns out that this is true for any n. You just get these marvelous cancellations because of all the signs from the permutations, and that allows you to express the determinant as essentially a product of terms. So you have a whole bunch of terms that you can calculate easily, and then you multiply them together. And so, okay, so then you can just basically do multiplication. Multiplication is a lot easier than sums. So the permanent is exactly the same as the determinant. It's a much easier expression, just there's no signature. So all of the terms are positive. And so if I were to naively do exactly the same procedure, turning all my minus signs to positive signs, then it's really obvious, right, that I get these terms that are adding instead of subtracting, and that's a problem. And so naively, you just have to add up all n factorial terms. There are more efficient algorithms than that, but generically, no efficient solution to the calculation of the permanent is known. They all of the algorithms that are classical are exponential in the size of the matrix.
Sorry, could you remind
sure.
me where the permanent comes up?
Where does it come up?
Yeah. So could you remind me where the permanent comes up? I mean, obviously you
Just give me one more slide on.
Okay.
Oh, wait a second, it's already here. Here we go. And I will give some examples. So I might as well get right to that. I mean, the complexity class is sharp P. It's similar to NP, but it's basically this, just really roughly, it's the class of problems that you that involve counting lots and lots and lots of things. So anyway, the permanent comes up in a number of other other problems that are in sharp P are given here, but in fact, enumerating the number of perfect matchings or counting, if you like, the weights of those perfect matchings is in fact the permanent. So that's a very generic setup. And let me just show you, because that was such a great, amazing segue. So one way to write down the permanent is to assign some n by complete bipartite graph with the vertices on the left side labeled by, say, the rows, and the vertices on the right side labeled by the columns, and then the edge weights correspond to the matrix elements from row to column, and then you can look at all of the perfect matchings of this graph. So a perfect matching is that every vertex is incident on a single edge, and then just count up all of the different products of the weights associated with those perfect matchings. So here, perfect matching corresponds to the 3 blue lines. I hope you can see blue versus black. I can't see red, so I just chose blue. And so the first one, you have W00, W11, and W22. So the total weight is the product of those. And then it's really easy to sort of run through and show that there are 6 different perfect matchings for this bipartite graph. Each of these has a unique weight, and then they sum up all of those weights, and that is literally the permanent. And then there's another way to think about the permanent, which is to assign the actual matrix that you want to find the permanent for. You associate that as to a graph, and so that's literally the adjacency matrix of the graph. And then these are the edges associated with that. And then you consider all of the cycle covers of this, directed weighted graph. And so cycle covers are all the subgraphs that include all vertices once. And so here's one, right, with all of the self loops on the outside as cycles. There's this one, which this self loop, and these two, et cetera, et cetera. All of these have distinct weights. Add them all up, that gives you the permanent. So the fastest known algorithm is due to riser. It scales like 2 to the n times n, and that's the best known algorithm right now. So part of what I was hoping to do is to use some new graph constructions and see if I could improve on that, and you'll see how that goes. But really interestingly, you can approximate the permanent in polynomial time efficiently for a subset of graphs, or so I should say a subset of matrices, either non-negative matrices with non-negative entries or positive semi-definite matrices. In poly, the number of operations in the size, and also in 1 over epsilon, and that sounds pretty good, except for the fact that the error is multiplicative. So you really have epsilon times p, and for a generic matrix, where the elements are on the order of 1, maybe Gaussian distributed around 1 or something, then this is an exponentially large quantity, and so your error is effectively exponentially large. And as far as we know, there's no examples of approximate algorithms for approximating the permanent to additive error, or for matrices that are reals or complex. So it's sort of an open problem. I got into this problem from the quantum side, where there's a problem called Boson sampling, and there are claims that the Boson sampling algorithm, even though it's not a universal algorithm for quantum computer, it still is something that can be done that shows quantum supremacy, that there's no classical algorithm that could calculate the Boson sampling output probabilities. And I wanted to spend some time on that, but I really just don't have the time, so I'm just going to show you some pretty pictures. The Boson sampling problem, if you want a real world context, photons come in one side of a big optical apparatus with beam splitters and mirrors and phase shifters, and they come out the other side, and your task is to drive, if you like, the distribution of output probabilities of those photons after they've gone through. you can sort of think of this as some great big unitary, which maps inputs to outputs, and so that's kind of like a quantum algorithm, even though it can't itself be a universal algorithm. And then I have a bunch of things that I can't talk about. But basically, because they're bosons, they're totally indistinguishable, and so any input state or any output state you have to symmetrize explicitly, because a boson that goes in here and a boson that goes in here come out maybe like that, but they might also come out like that, and you can't tell the difference. And so you have to explicitly symmetrize, and the process of doing that means that the probabilities of the outputs require you to calculate the mod squared of a permanent, and you have to do a lot of them. And that's kind of the reason why it's hard for a classical computer to do, because doing this is exponentially hard. Okay, not finished my introduction yet, but almost. All right. So for a 2x2 matrix, it's really easy to show. Right, the permanent of this matrix is just a determinant of this one. Right, if I just take map B to minus B, I get A times D minus C times D. So that's just the permanent. So that's great. But it turns out that there's no way to sign the entries of a matrix such that the permanent is equal to the determinant for any larger matrix. So we're completely stuck right there. However, it was proven by several authors just a few years ago that instead you can calculate the determinant of a larger matrix with the matrix elements defined by the original matrix. I hope you can see that large enough. The x's are the matrix elements of the original matrix of minimal dimension 2 to the n minus 1. So if the original matrix dimension is n, then it's 2 to the n minus 1. And this just leapt right out at me. This is a directed hypercube graph with some self loops, and it jumped out at me because I'm like, wow, this is 2 to the n dimensional. That's just perfect for quantum algorithms, right? You could imagine thinking of this as an operator on qubits. So that's literally my entry point into this problem. And I don't know if you can tell, but I think some of these loops are red, and this is an instance of a cycle cover, I think, for this graph, because the top vertex of this hypercube is mapped to the bottom vertex. They're seen as the same. So once you get to the bottom, you're essentially back at the top again, and so you have a cycle. But then it was also noted by these other authors, Huttenhain and Gang, that you can think of this directed hypercube graph with these weighted edges as the so-called binary algebraic branching program, because you can think about the traversal from this top vertex to the bottom vertex as enumerating all the different paths that you traverse from the top to the bottom, enumerate all of the entries of the permanent. So I kind of exploded this for you to see. So that you have a path that's W00, W11, W22, but then there's also a path W00, W21, W12, which is just the switch. And so this directed hypercube is a way to enumerate the permanent. But it wasn't, they didn't really follow up on that. But I just thought, oh, that's neat. Let me explore where that idea might go. So I just got rid of the self loops, and I thought about the hypercube vertices as labeled by bit strings. So an n-dimensional hypercube, you've got n long bit strings. All the vertices are, and I drew it this way so the vertices kind of form layers of constant Hamming weight. So the top layer has 0 Hamming weight for the bit strings. This is Hamming weight 1, Hamming weight 2, Hamming weight 3, and of course this generalizes to any dimension. And then the weights on the edges are tied to, so the first index for the weight is tied to which layer it comes from, which layer the edge comes from. So this is coming from layer 0, so that's the first index 0. And then the second index is telling you which bit gets flipped in this bit string. So for example, here you have the bit at the 0 position gets flipped to the 1, and so that's the 0. Whereas the bit that's in the first position, that gets flipped, and so that's W01, et cetera, et cetera. So there's a unique labeling for the edge weights, and it turns out that labeling is exactly the same as what was used by Huttenhain and Gang, but they didn't make a connection to bit strings. And then you can either map, you can either decide that the 111 bit string is just the same as the 00 bit string, or you can just add another directed edge that takes you from the 111 to the 000 to complete the cycle. So then I can write down a Hamiltonian or adjacency matrix for this graph, and it has quite a simple form. Basically, I enumerate over all of the possible bit strings. These are the bold i's, and then I map from I to some other bit string where I've raised the spin value from 0 to 1 on one of the entries. So I sum over j over 0 to n, and I'm raising the spin value from 0 to 1 somewhere with some weight, which is given by the Hamming the Hamming weight of I and the index J. And just if you're not, so I'm doing this as a physicist because I can't help it. So I think about spin raising and lowering operators, and that's what I'm doing here. Sigma I plus raises the spin value from 0 to 1, right? So if you input with 0, then you output 1, and sigma minus lowers the spin from 1 to 0. And then the 0, 1, and the 1 are just look like this, which I don't use. And then here's my last edge that takes me from the all 1 bit string to the all 0 bit string back to the top. And so there's my model, and then I'm going to wave my hands and say, well, it's really obvious that this enumerates all the possible paths of a permanent because I can once I've raised a spin from the 0 to 1, I can't raise that again because the raising operator on the 1 is exactly 0 because the overlap of 0 with 1 is 0. And so that means that as I'm enumerating all these, any place where there was a 1 immediately doesn't factor in, and so I'm going to see all possible combinations of all the weights, all going from 0, 0, 0, all to 1, 1, 1. Okay, that was very hand wavy, but that's, I think, hopefully by using examples you can see where I'm going. Okay, so then a whole bunch of consequences to this that I thought were pretty neat. So one is that m twiddle is a cycle that takes you from 0 on n plus 1 applications back to 0 again, which means that that the nth power of m takes you from 0 back to 0, and then you can think of this as sort of an n-fold product of non-square matrices with dimensions n choose I plus 1 by n choose I. And then whether I use n plus 1 or n applications depends on whether you map 0, 0 directly to 1, 1, 1 or have the extra thing. But anyway, the consequence is that this is just a bunch of matrix vector multiplications, and you can enumerate the complexity of doing those operations, and you get exactly n times 2 to the n. So okay, whatever, it scales just like Reiser's algorithm, but it's really way easier, right? You literally just do matrix vector multiplications and you get the answer. The other cool thing is that because m to the n, I'm forgetting about the plus 1, is the cycle, and we already know that 0 is an eigenvector of m to the n, then that actually means that all the eigenvalues of m twiddle are just nth roots of m, are just nth roots of that eigenvalue. So if lambda is an eigenvalue of this power, then that means that there are n eigenvalues of m twiddle that are just the nth roots. And we already know that the permanent is an eigenvalue of m to the n, and that means that I have the eigenvalues of m twiddle are just the nth roots of the permanent. And furthermore, the eigenvectors are really easy to construct. They're just linear combinations of successive powers of m operating on the 0 vector. So basically, you can totally, you just can write down the eigenvalues for this problem. And what's even cooler is that these are the only non-zero eigenvalues of m twiddle. That's a little bit, maybe it's harder to see why it's the only ones, but it's really easy to see what's going on. So m to the n you can write as basically a block diagonal matrix with blocks of dimension n choose j, and each of these blocks has exactly one eigenvalue, which is p, which is the permanent. And so you can write that. So here are the definition of the blocks. They just sort of m twiddle to the n minus j power on 0, and then the adjoint is 0 times m twiddle to the j. And then if I write down the eigenstates as m to the n minus j on 0, then it's pretty obvious. Then if I operate with this on that eigenvalue, I get p. So every single block has exactly one eigenvalue, and it's p. That's not 0, and all the other eigenvalues are 0. So that's kind of nice because that means that the nullity is exponentially large, but if that's true, then maybe there's a hope that one could try to do some kind of reductions on that big matrix, preserving the non-zero eigenvalues, but throwing away lots of zeros. And it turns out that that's exactly what Gaussian elimination is doing for the determinant. And so I wanted to talk about that part, and then I'll come back to I'll come back to the permanent after. So let me just do a quick side trip to the determinant. Back on this, and I have to introduce a new concept there. Okay, so let's go back here. We have a spin model. We have its bit strings, and we think of them as spins that can be in 0 or 1. Well, it turns out that there's a well-known mapping between spins and fermions in one dimension exactly, which is the Jordan-Wigner transformation. And so I'm just using some physics stuff, and I'll get back to the graph in a second. So basically, spins on the same site anti-commute, but spins on different sites commute. whereas fermions anti-commute always, no matter how far apart they are. But you can introduce these odd kind of mappings between spin raising, lowering, and the Z spin operator to fermions that allows the fermionic algebra to be anti-commuting everywhere and still satisfy the algebra for spins. And so let me just explain what's going on here. If you're not familiar with this, this is kind of gross looking, and so I'm just going to explain it what's going on. So the spin up operator takes you from 0 to 1, and the F dagger is taking you is creating a fermion on side J, and this lowering operator is basically deleting a fermion. So this is an annihilation operator. It's taking you from 1 to 0, and then the Z operator. This is the density, Fj dagger. Fj is like the density operator. It asks you, do you have a fermion there? It's kind of like a searchlight. If a fermion is there, then delete it by annihilating it, then recreating it, and that counts it. So if you have a fermion there, then you get a factor of 2 minus 1 that gives you 1. And if there's no fermion there, then you're annihilating the vacuum and you get nothing, so you get a minus 1. So you can see the eigenvalues of the Z operator straight. Now, with this thing is a bit funky. Basically, what it's saying is, in order to account for the non-locality of fermionic anti-commutation, what you're adding is an extra phase that counts how many fermions are left of the position where you want to create the fermion or to annihilate the fermion. So it's kind of like a whole string. You have to account for all the strings of fermions. Let me just give you some examples. This is a very busy slide, but there's a lot of cool stuff going on here. Okay, so imagine I'm going back to my hypercube model. This is an example for d equals 3, or n equals 3. So now this is going to be fermions. These zeros don't represent spin anymore. They represent, is a fermion there or is a fermion not there? So if it's 0, that means there's no fermion, and if there's 1, that means there is a fermion. There's no fermions anywhere. Now I've created a fermion here on the 0 position, and then here I've created a fermion on the 1 position, and here I've created a fermion on the 2 position. All good. But let's look at this path. I'm going from 0, 1, 0, where there's a fermion on the 1 position. And now I've created a fermion in the 0 position, but you see there's one left of it. And because there's one left of it, that has a minus sign. So the minus signs come out automatically just from the Jordan-Wigner transformation. And you'll notice that if I look at this path, this is kind of the reference path with the 0, 1, 2 bit string. Well, then the other one, which is the 2, 1, you notice that this whole path is a minus sign overall because there's a minus sign on this edge. Likewise, here I have this one is minus. This one with one permutation is plus. This one is plus overall because you have 2 minus signs. This one's minus. So there's an equal number of minus and plus trajectories overall, which is what you want for the determinant. And furthermore, the edge weightings are unique. I just want to say that this is a kind of an unbalanced signed graph in the sense that there's no vertex switching that I can use to turn this into a totally unsigned graph. What I could do, right, you could say, oh, look, I can just replace minus W10 by plus W10, and I could replace minus W21 with plus W21. That looks pretty good, but if I try to do that with W11, turn this into plus, this one becomes minus. And so there's also no kind of like Schur style reweightings of the weightings, so re-signings of the weightings that allows us to become all positive. So you can't just map fermions into bosons or map the determinant into the permanent. Okay, and then the next thing I want to mention is that there's a really neat thing you can do at this point, which is row reduction, which what allows us to eliminate vertices and edges in this graph while preserving the eigenvalues. And you do that by basically the analog of pivoting. I can write this matrix M twiddle as A times B, where A is the so-called pivot matrix or a matrix in reduced row echelon form, and then B is like the original matrix M, but with some rows deleted. And it turns out that there are some factors in this reduced row echelon form that allow you to do that and still get you back M twiddle. And these are exactly the factors that you need in Gaussian elimination to eliminate certain rows, to make certain zeros in rows in the calculation of the determinant in the very first year linear algebra way. Okay, and so I can just eliminate those rows of my B matrix, and that eliminates the vertices of the associated graph. And here's just a really quick reason why the non-zero eigenvalues are preserved. I can write M twiddle as AB on psi. That's obviously lambda on psi. If I just multiply on the left by B, I get BA on B psi but this is still lambda b psi, and so that means that BA is an eigen operator for psi prime, or psi prime is beyond psi, and B reduces the dimension of psi. So okay, so I did that, and what I'm really doing is I'm eliminating these vertices and eliminating the edges associated with them, but I still need to account for the fact that there were these paths. And so what that means is that the edge weights that are left over are rescaled. For example, W11 also accounts for this path that got deleted by the elimination of those vertices, which had a W01, W10 contribution with a minus sign, and there's the term right there. So doing this row reduction automatically reweights the remaining edges, and it turns out that this is the test part. That these reweightings are exactly the reweightings you get from doing Gaussian elimination. So then you're left with this graph, which has far fewer paths. There's only now 2 paths. As we used to have 6. You can do it again by removing this last vertex, exactly the same procedure, and then you're left with just 1 path with this as a rescaled edge, and then a second layer of rescaled edge, and again exactly the same procedure. It just now is sort of a graphical basis for doing this reduction. And that's kind of the name of the game, right? Is trying to reduce the work and still do the calculation. Okay, so then I'm like, all right, let's try to do this with bosons, or sorry, let's try to do this with spins. Back again, and it turns out you can't just eliminate this vertex and this vertex and this vertex and have a consistent reweighting. But what you can do is you can reduce all of the vertices in a given layer except for 1 at a time. So you can still do n of these row reductions, but just layer by layer by layer, removing all but 1 vertex. And so I can do that right here with this row echelon form matrix. But here's the kicker: when I do that with bosons, I generate a new edge that wasn't there before, because it has to account for this path and this path that got eliminated by the deletion of these 2 vertices, and that can only be accounted for by introducing a new edge. And so, like, right away, you're like, this is not going to work for arbitrary n, because in the worst case situation, sort of halfway down the hypercube, I've got n choose n over 2 vertices, and I'm going to have n choose n over 2 additional edges that I have to account for, and that's just a ton of work. So that's still an exponential amount of work. I mean, I shouldn't be surprised, but I was disappointed, let's just say. Okay, and then, but then if you work it all out, I did a careful accounting for all n, and you still do get an asymptotic scaling of n times 2 to the n for that algorithm, just with a little bit more work, in finite n. Okay, but you can map spins to bosons also. You don't have to only map them to fermions. There's a mapping from spins to bosons, but using the Schwinger representation. So I'm throwing another quantum field at you, but whatever. Okay, so in the Schwinger boson representation, you map spins to 2 flavors of bosons, an A-type flavor and a B-type flavor, and so then a spin up operator corresponds to deleting a B-type boson and creating an A-type boson, and the lowering operator corresponds to annihilating an A-type boson and creating a B-type boson, and then the Z operator is the density of A's minus the density of B's. Okay, so these ones all satisfy the standard bosonic commuting Lie algebra, but then there's a really, really important additional condition that Schwinger imposed, which is that you can only have exactly 1 boson on every site. It's either an A-type or it's a B-type, but there's exactly 1. And so then that means that you're just changing the flavor. You're either changing from A to a B, or you're changing a B to an A. And this actually corresponds to so-called hardcore bosons, because if you have this unit occupancy condition, that means if you try to put an extra boson on there, it immediately says, no, I'm sorry. So these are really hardcore bosons that I'm mapping to. And it's kind of interesting that hardcore bosons have come up before in the context of symmetric powers of graphs, and I might have some time to comment on that later. Okay, so then we can rewrite the eigenstates of we can write down the eigenstates of these block diagonal operators in the bosonic representation. So let me take a little bit of time to get there, because I think you're gonna freak when I get to the answer. Okay. Okay. So let me just do things a little bit explicitly here. When I apply m once to the 0 vector, I get W0001 plus W 0, 1, 1, 0. That's like the first leg of, say, a square lattice. So W0, 0 goes to there, and then W0, 1 goes to there. And then now what I'm going to do is I'm going to write those operators in terms of the Schwinger representation. So first of all, my vacuum state is just B-type bosons. I create a B-type boson on 0, B-type boson on 1, operating on the vacuum. That's my vacuum state. This is the particle vacuum, but this is kind of like my particle, how shall I put it? My zero vector is just B-type bosons everywhere. Okay, so then if I want to put a 1, then I need to in the 1 and the 0 position, I need to delete the B-type boson and I need to create an A-type boson. And if I want to create a 1 here in the 1 position, I need to delete that B-type boson in the 1 position and create the A-type boson there. You all cool? Okay, and then I write that out. I just expand it out. I'm not doing anything fancy here. But I have a factor here, B0, B0 dagger. And I can write that as 1 plus B0 dagger B0 because that's the bosonic commutation rule. And B0 commutes with the B1 dagger and immediately kills the particle vacuum. So this term I can just throw away. This one, I have a B1 and then a B1 dagger, but there's a B naught dagger in the middle. But who cares? I can just commute that through because B1 and B naught always commute. So I just push that one through, and then I can then write the B1 dagger that's left over as 1 plus B1 dagger B1. And again, this one just kills the vacuum and it goes away. Then I can write the final expression as A naught dagger B1 dagger plus A1 dagger B naught, which honestly you could have just guessed right away, because if I have 0, 1, then I want an A type in the 0 position, and I want a B type in the 1 position, and likewise over here. Okay, so I can just literally just write that down and say, the 1, 0 corresponds to an A type in the 1 position and a B type in the 0 position. Okay, yeah. Okay, so now I'm just going to copy this thing and I'm going to do it again. Oh no, what I'm going to do is I'm going to say, well, check this out. I can actually write this thing in a totally separable way. Let me just pull this. I'll pull out W00 A naught dagger plus W01 A1 dagger times B naught dagger plus B1 dagger. And then if I expand that out again, I get 4 terms. But these terms totally go away because of the hardcore boson condition. And then if I look at M squared, I can totally just write the M squared as W10 A0 dagger plus W11 A1 dagger times a similar thing here. And I can just write that as a product state. And nevertheless, that's still equal to the permanent because I have the hardcore condition and some terms just automatically drop out. And this obviously generalizes to arbitrary n. I can literally just write down the permanent as the sum over A0 all the way to A n minus 1 dagger. And then for different choices of W's, it layer by layer by layer. So this is layer n minus 1, then you have layer n, then layer n minus 2, all the way down to layer 0. And so very oddly, the permanent kind of boils down to just a product of sums, which if we could write the creation operators as just numbers, then literally that would just be an n-cubed problem. But unfortunately, these A daggers are not numbers, and then we can't. But there's this really kind of intuitive form that was a bit surprising. And then if we just go back, well, wait a second, in hindsight, then maybe the fermionic problem and for determinants is exactly the same. And that's totally true. If you just look at the 2x2 case, you could write that as this sum with just F's now instead of B's. And then again, the ones that correspond to try to creating 2 fermions on the same site just automatically go away, not because they're hardcore bosons, but because of Pauli exclusion principle. So automatically you're not allowed to have 2 fermions on the same site. So you're just left with the 2 terms. But you have F naught dagger, F1 dagger in this one, and you have F1 dagger, F naught dagger in this one. And if you want to write them in the same representation, then one of those has to get flipped. So let's just choose the representation where F1 is first and F naught is second. Then that means I have to turn this one around. And so I get W00 W11 minus W01 10. And literally that you can sort of think of the signs in the determinant arising just from the fermionic anti-commutation in that model. So there's a very, very close and deep connection between determinants and fermions, and that's why non-interacting fermion systems are classically simulatable, because the determinants are easy to compute. Whereas bosons, which is how I got into the whole problem in the first place, are hard to compute because of this permanent problem. But it does seem very odd, right? Because they're on exactly the same footing, and somehow one becomes exponentially hard, and the other one's easy. And then the question is, well, what does fermionic graph reduction? When I'm doing these row reductions for my graphs, what does that look like in the fermionic representation? Well, I start with this thing, and then the row reductions tell me, well, really, I'm just reweighting W11. So I'm just pulling this factor out, and then I have an F dagger, W00 F naught dagger. And then I don't have to do that multiplication. I don't have to worry about the fermionic, Pauli exclusion principle. All I do is multiply this factor times this factor, and I'm done. So that was neat. And let me just show for the 3x3 case. I mean, it's a bit more involved. I'd have 3 terms. But then if I'm just literally putting in what happens in the graph reductions, then I'm mapping, the W. I get rid of W20 completely. I get rid of W10 completely, and I reweight W21, W22. I reweight W1 and W21 and W22. So I read it like this, and that just gives me a product of 2 things that looks just like 2, but looks like a 2x2 again. But then I do again a second round of row reductions, and that just rescales W22. And so with fermions, I never actually have to do the expansion of this disgusting thing at the top. I just rescale my parameters, and then it just ends up with a simple product. The hope is that there's an ingenious way to do this for bosons that allows you to maybe find a more efficient algorithm for solving for the permanent. So in the case for 2x2, it's really simple, but for the case for the 3x3, the rescaling generates a sum of 2 terms. And then you end up getting a sum of terms that involve sort of 2x2s, and you have to add all those up separately. When you work it all out, which I'm waving my hands now because I'm running out of time, you do get the permanent, but doing so always requires summing up a whole bunch of smaller chunks of n-1s, n-2s, and when you work through all the details, it turns out that row reductions for bosons corresponds to n-1 times 2 to the n amount of work. So I haven't, unfortunately, improved on this at the moment, but here's the thing: there's a lot of different ways of choosing vertices to eliminate and choosing parameters in the reduced row echelon matrix, and there's not a lot of guidance, about what one should choose, and it's entirely possible that a very neat choice, maybe with some minus signs, would allow an improvement in the complexity of solving this problem. Okay, so that's the thing about the classical piece that I want to tell you, and then I have a whole pile of things that I want to tell you about quantum algorithms. But I'll just kind of throw the slide up and talk about sort of the problem posed as a quantum algorithm problem. So one thing that seems really great about this problem is that the dimension of m twiddle is a power of 2. So that seems to lend itself well to qubits. The matrix elements are very easily indexed by address. They're just basically based on Hamming weight. M is n sparse. Every single row or column has at most n elements. The permanent is the maximal eigenvalue of m to the n. So that seems like a great, easy thing for finding, the maximal eigenvalue of a matrix using something like phase estimation. Or maybe you could just, directly simulate this problem using hardcore bosons, and hardcore bosons already, are easy to make in a lab. But here are the big buts. Big buts are m twiddle is not a Hermitian matrix, and besides, the eigenvalues are not real. They're nth roots of p, and then m to the n is still not Hermitian, even though the eigenvalues are all real, and it's not sparse. It's actually, really not sparse. It's exponential number of elements in the rows, and then in the Hamiltonian for hardcore bosons, if you want to do hardcore bosons, is not number conserving, which is really hard to do a controlled way in a lab, and also the parameters in the matrix depend on how many bosons are there, and so basically I have a whole bunch of things that I want to tell you about how to embed the M matrix into either using linear combination of unitaries like we just heard in the previous talk, or or embedding in a larger unitary, or in a larger Hermitian matrix. And the reason I wanted to tell you all of this is because these are amazingly good techniques for encoding quantum walks. And so I had a dual purpose there, but I am out of time. And so I'm just going to leave it there, and then I'll post my notes. And if you want to take a look then and talk, that's great. But otherwise, thanks for listening.
For a great talk, David. Any questions for David?
Just the quantum part is interesting, but just about the classical part, you were looking through the Boolean lattice and getting a complexity for a classical approach that sort of matched Reiser's complexity. But it seems to me that you need to store all those intermediate results. You have exponential storage.
Yep.
Halfway through, right?
That is a bit of a downside.
Okay. But the running time, I guess, is not a function of that store. It's not pumped up by that exponential storage, is it?
Right. And I don't know a way to mitigate that, honestly.
Yeah. Thank you for the talk. Really nice. Thank you.
Any other questions? All right, if there is no other questions, let's thank our speaker again.
Yeah.